In this video, we will model communication channel effects in MATLAB. In general, any communication channel can be represented as a convolution with input signal xt, output signal yt, and then the channel is modeled as the impulse response ht. Therefore, the relationship is yt equals to ht convolved with xt, or it can be written as xt input signal convolved with the channel ht, where xt is the signal at the transmitter, yt is the received signal at the receiver. Let's look at an example, MATLAB example for convolution. It is convolve x example.m. So we open that MATLAB script. TS is the sampling period. Sampling period is 1/100. Suppose that's 0.01 second, 10 milliseconds, and time is 10 seconds. T is the time vector from 0 step size of TS to time, the end time. Define the impulse response. Here is an exponential function, and it's a decaying exponential function, e to the power negative t. X is my impulse, it is the input signal. So here it's we are defined x is only have two spikes. X is all 0 except at 1/TS, that's we have a value of 3. Another is at 3/TS that has a value of 2. Okay. Then we do a convolution, y equals convolved h with x. Then on the figure we plot with time vector t, what is the input signal x, with time vector t, what is the impulse response, and then t, the output taking the length from 1 to length of my time vector. So here comes the result on the right, and we can see that the input indeed we have only 2 spikes, and with the amplitude of 3 and 2. The impulse response is an exponential, e to the power negative t, therefore it is decaying like that. And then a convolution of those two signals is that we have the first impulse spike with the impulse response with like this peak, and then we have another spike of input with the impulse response. So it's starting at time at 3, so it goes like that. Now I can change the impulse response. Suppose impulse response change to a sinc function, and then run that. So this is the impulse response, it's a sinc function. At the output, we have this sinc function. It is one is multiplied by this first input spike. The second is the impulse response multiplied by the second spike. So the convolution, it looks like that. We have two summed together, give me the output. Similarly, we can see if I change the impulse response to a sine function, here h equals to sine 25 times t, and that's the figure with the impulse response sign, and the output looks like this. Now let me use a sinc function as the impulse response. So h here is equal to the sinc function, and I use a Gaussian random noise, a white Gaussian random noise, as my input signal. X equals to rand n of size t, t is the time vector. Then convolve this input with impulse response. I have the result here. So here is my input. It's a white random Gaussian noise. The impulse response is the sinc function. The output is the random noise convolved with this sinc function. That gives me a result. It shows like this at the output. Now I want to see the channel effect of this sinc function. If sinc function in time domain is a sinc function, and then this channel effect, what will give me is it will be a low pass filter in the frequency domain. Basically, a sinc function in the frequency domain is a rectangular function. The rectangular function will filter out out-of-band frequency. So let's look at the spectrum of that. So we're using plot spec. By the way, plot spec is a MATLAB script from this directory. So let's just open that, plot spec.m. And you can see plot spec, it's a function. It's a design function. We designed that function. With x is the signal sequence that I want to show the spectrum. Ts is the sampling period. Okay, and then what this code does is use the FFT, Fourier transform, then to plot that with the magnitude, and also plot out the waveform in time domain. Now let's use this function plot spec. So at figure 2, plot spec the input signal x, t of s. So here's the input signal. That is a white noise. The lower picture is the magnitude. Because it's white Gaussian noise, therefore I have the magnitude across all frequency. Figure 3, plot out the spectrum of the input response h. So here is the result. The top picture is the sinc function in the time domain, and in the frequency domain, we see the magnitude. The frequency domain, it's a low-pass filter. It's centered at the frequency 0 dC because FFT shift is applied in the function, and we see this rectangular box. Then on figure 4, we will plot the output. This is the received signal. That is the input signal, a random noise going through a low-pass channel. And here is the result. So the top picture shows the time domain signal, and the lower picture shows the received signal. Indeed, it is a noise, but it only has low frequency component. Now let's look at how to model a fading channel. If I have a transmitter here, that's my transmitter TX. I have a receiver here, RX, with an antenna. I have a channel, we have a direct path, and suppose I have another multipath. This is a reflection from the ground. I have two paths. They are arriving at the receiver. So the signal YT equals to XT. This is from the direct line of sight path, XT times the channel attenuation is alpha 1 times e to the power j 2 pi fct. Okay, this is the carrier frequency. And then I have another one, which is the multipath is the delayed copy, is ht subtract tau. Tau being the delay, relative delay compared with the line of sight. So this is the line of sight. This is the non-line of sight. It's a delayed path. Multiplied by another attenuation alpha 2, channel e to the j 2 pi fct subtract tau. So we have two paths coming in. One is line of sight, the first one. The second one is this non-line of sight component. Now we know for an input signal xn or xt, we have a delayed element. This is because of the convolution. We have a convolution convolved with the impulse delay. So ht, without any of these amplitude or attenuation, in this case I have the ht will be, one is convolved with just impulse response, a spike. Another one is a delayed version. And this relative delay from here to here is time tau. Okay, and that is alpha 1, this is alpha 2. Now, that's the convolution, convolved with ht. Suppose I am working with a narrowband signal. Narrowband signal meaning that my symbol period is quite large. The symbol period is quite large. Therefore, when I delay a time tau, it is still within the same symbol. Let's say the first symbol from here to here, second symbol, third symbol. But this delay compared with the symbol period is quite small. Maybe it's just delay a little bit here to here. It's narrow band. And in this case, I can approximate this equation equal to xt alpha 1 e to the j 2 pi fct plus this is also xt. It's narrowband assumption, so the delay does not affect too much. So it's alpha 2 e to the j 2 pi fct subtract tau. Now, when I say narrowband signal, that means the signal frequency is small, the symbol frequency is small, and the symbol period is large compared with the delay. So therefore, I can approximately, looking at xt, taking out of those two paths, and assuming those two paths, the symbol, they will arriving at the receiver at the same time, synchronized. But the only difference is that this attenuation from different paths, they are different. They add together because I have two exponential adding together. Sometimes they can be adding together positively. Sometimes they are adding together negatively. They cancel out each other. That gives us the fading effect. So in this case, a narrowband signal, I just changed the convolution into a multiplication. Multiply on each symbol period, symbol point, and this ht is this weight, this complex weight. That is my ht. Okay. Again, why I can do this multiplication? Because I assume it's a narrowband signal. If it's wideband signal, then you have to consider this convolution, and then you need to put in this t subtract tau onto the symbol and onto each different path. Okay. Now what I want to do, I want to, using MATLAB, to see the fading effect of ht, channel ht. At the receiver side, we will do a down conversion. Therefore, the received signal is yt multiplied by e to the power negative j 2 pi fct, fc being the carrier frequency. So that is xt, and then alpha 1 e to the j 2 pi fc subtract fct. So we bring that to baseband. So this is 1. And the second term is alpha 2, and then we also do this down conversion. So what's left is e to the power j 2 pi fc negative tau. Okay. Therefore, my channel has two parts. One is the line of sight part with alpha 1. The other part is some multipath. That is a j, and then we have this random phase. Let me just call this alpha 2 because the tau is a random. It's a random delay of the second path, incoming path, multiplied by this carrier, and we have this this phase. Now, because the carrier is usually quite large, even though tau is very small, the delay is the distance between those two paths divided by the speed of light. But because of carrier is quite large, as we always said that, and I do have a quite large phase. It's non-negligible phase here. It's we call it phi 2. Let's look at the general case. The general case is that I don't have any line of sight, so I do not have a dominant path coming in. So I got a transmitter here, I got a receiver here, but there's no line of sight. Everything is coming as a reflection, bounced back by some objective. And the model here for me at the receiver is that I assume that the path is incoming all over within the direction from 0 to 300 degree. It's just coming everywhere. And with all these incoming paths, they have the same distribution in this angle. Also, they have same distribution of their amplitude of each path. So this is called the Rayleigh model, Rayleigh fading model, Rayleigh fading model. Now, if I do have a line of sight, suppose I have a very strong line of sight heat, this becomes a Rayleigh fading. Rayleigh fading is just a special case of Rayleigh fading. It just have a dominant line of sight. You will have all these amplitude is modeled by alpha, alpha 2, alpha 3, alpha 4, but alpha 1 is particularly large. But if I don't have that, it's Rayleigh fading. Everything comes in with comparative amplitude. This channel is a Rayleigh fading channel, and this propagation model is called the Jake's model. And a Jake's model, you can think that as a case when I have a receiver in an urban canyon environment, in downtown, or the receiver is indoor, so the receiver does not see the transmitter. You don't see the transmission tower, but everything is assuming there are the same strength multipaths coming all over the direction. Then I have a Rayleigh fading channel. Now, if you look at the channel response HT, in this case is we sum over all these paths, I path alpha 1 times e to the power j phi sub I, phi being the random phase, Okay. Now, when does fading happens? When does fading happen? Is when all these paths, some of the paths, or all these paths will be time varying. Or in Jake's model is that my receiver or the transmitter will moving. Let's say the receiver is moving with the direction of here and is moving with the speed of v. The effect of the receiver moving is that I have a Doppler shift of all these paths with all these incoming signals with their own carrier frequency. I'll have a Doppler shift. So let's say if looking into an incoming wave coming here, if my moving direction is just toward that incoming wave, then the Doppler shift will be a positive shift. So we have a Doppler frequency. You're adding the Doppler frequency. It's a positive Doppler frequency. If I have considering some path is coming here, but you are moving from left to right, so you are moving away from this impinging signal, so the Doppler shift will be negative. Okay, so that is we have this moving part. Now this Doppler shift is we model that in here. That's sum over alpha I, and then because of this frequency shift, I have e to the j 2 pi f sub d being the Doppler frequency. And because I'm coming all over this direction, so if this, let's say this coming path, we have an angle here is theta I. So the Doppler frequency will be fd multiplied by cosine theta I t. And then I have this random phase, e to the power j phi I. Okay, so cosine theta I from 0 to 380 degree. So it's 0 to 180 and then to 360 degree. You go in a circle. And then this cosine is in the range from -1 to 1. 1 being the largest Doppler, use FD, it's positive FD. -1 being the smallest Doppler, that's negative FD. You are actually moving away from the transmission source. But in the Jake's model, theta is uniformly distributed between 0 and 360 degree, between 0 and 2 pi. I also have this phi. Phi is another, that's the random phase. That's due to the path delay. That's due to some refraction effects here. I also model phi as a random variable, uniformly distributed on the intervals 0 to 2 pi. So for simplicity, let me remove all these alpha i's. Suppose every path coming with the same power. And alpha I in reality, it can be any complex number. Now if it's being complex, you just absorb the phase into this random phase here. But let's just remove that. So the simple version is I have all these I path, incoming paths, with the first exponential term caused by the Doppler shift, Doppler frequency, and the second one is the random phase. Okay. Because I have this Doppler shift, it's caused by it moving, and I have a time variable here, so I can plot a picture of ht being a function of time, because as time goes by, I actually moves, and in this case, that will show sometimes all these components, multipath components, they will add constructively. I'll get a large ht. Sometimes they will add destructively, so I will get a very small ht, and even nullified, I get 0 ht, so I will be in a deep fade. Let's look how I can model H in MATLAB. So we have here the time vector is generated as before. Theta is the impinging path angles. Theta is a random variable, uniformly distributed between 0 and 2 pi. Suppose I have 100 paths coming in, so I have a rand 101. The length is 100. And then I have phi. Phi is the random phase. This phase is also a random variable uniformly distributed between 0 and 2 pi. I have altogether 100 phis. Fd is the Doppler frequency. Doppler frequency, I'm picking 10 Hertz. Okay. H is the channel. This is the narrowband channel, ht. I want to plot out H as a function of time. So H is first I define as a zero vector of length of t. On each of those time instants, I am going to calculate hz equals to, this sum is first exponential. The first exponential here, this is exponential due to the moving part of your receiver. So I have the Doppler frequency here, Fd, multiplied by cosine theta, and on each element of my time vector times t of z. The second term here, the dot product, the second term here is due to the random phase phi. So I have phi here, phi is with a length of 100. And then do the sum. So I adding together those 100 paths altogether. That will give me each hz, h on each time instant. Plot out the absolute value of h. H itself can be a complex channel, it's a complex number. So I'm plotting out the absolute value of h. On figure 2, it's the same plot the absolute value of h, but instead I'm doing the semi-log y. I want to see the logarithm on the y-axis, a logarithm on the amplitude axis. So let's run that. Okay, so here is figure 1, and that has a channel ht with some of the fading effects. Figure 2, here is figure 2. Figure 2 is the same channel, but we have this on the log plot. Now in this case, because my time span is not very large, it's only 10 seconds, and my frequency is using 10 Hertz. Here my sampling frequency is 100 Hertz. 100 Hertz is not large enough. I don't see too much change here. So let me change this Doppler frequency into a smaller one. Let's say I only have 1 Hertz. 1 Hertz. All right, so there we go. So here is the fading channel. Fading channel is kind of, I'm zooming in the previous picture, but because my sampling rate is low, so in this case I'm kind of zooming in, and I have a smaller Doppler frequency, and it kind of connect all these dots, so it gives you some continuous effect of this channel. That's this fading channel, and this is the channel fading channel, Rayleigh fading channel. Plot 2 is the Rayleigh fading channel in dB. Here I put grid on, and this is the Rayleigh fading channel. You've probably seen that in many different literatures, and showing you the channel effect of ht. Now I also want to see the frequency domain channel h. So figure 3, I plot the absolute value of FFT shift, FFT of h. So here is the spectrum of my channel. you will see this channel is concentrated at DC. This is because this channel span is from negative FD to positive FD. FD in my case is very small. It's 1 Hertz compared with my sampling frequency of 100 Hertz. So it's only here at 1% showing on this picture. Let me zoom in on this frequency here. So we can see, probably you can see a little bit a trend of that this distribution of this spectrum it's concentrated, has large power on two ends, at the negative FD and the positive FD. Now in the middle it's relatively small. It's relatively small with close to 0. This is consistent with some other examples that we can see from other literatures. For example, this is another Doppler channel, Doppler frequency shift caused the Rayleigh fading channel in time domain. And here is this same channel, but we zoom out so you can see more span of this fading channel. And then here, this is the frequency channel, the frequency spectrum of the channel. You can see in this case, the Doppler frequency is 10 Hertz. Therefore, the frequency shift from the carrier is with a span negative 10 Hertz to 10 Hertz. And then it's the same. We have this U shape. That is, I got a higher power concentration on the two ends, close to negative Doppler frequency and a positive Doppler frequency, but in the middle is quite large. Why do we have that? This is actually a standard spectrum according to the Jakes model. Now recall that according to the Jakes model, all these multipaths are incoming from with an angle, incoming angle from 0 to 2 pi. So they are uniformly distributed all over this direction. If this is the case, the signal coming from this direction will have high density. Coming from this direction will have high density. Now if you're counting the signal from this direction, they will have a low density. And it's also, you can reason that because I have a cosine function. It's a cosine function when theta is close to 0 and a pi and a 2 pi, even though you have a very small angle shift, the density of all these impinging paths are large. Here, if you spread those paths equally, and then you will have a less dense impinging signals. That's why we will have in the frequency domain, you will see a lot of concentration on this angle here, which is negative Doppler frequency, FD, which is all these impinging signals from here. And then I have another concentration at FD, which is all these impinging signals coming from at this angle, if my receiver is moving from left to right. The next example is a channel effect using the general convolution format. So the signal X convolve with my channel H and give me the received signal of Y. This example is from the book. So we have shown that in class as well. We have a filter. The filter is designed as a bandpass filter. So we have these. Filter is at the frequency 0.29, we have a rising edge. So from 0.29 to 0.3 is the transition from 0 to 1. And then the passband is 0.3 to 0.4. That's all 1. And then from 0.4 to 0.41, that's the falling edge. That's my range for the falling frequency. And then 0.41 to 1 is my stop band 0. So this is a bandpass filter. Because of my sampling frequency is 20 kilohertz, then 0.3, 0.4, and I have here is we have a passband between 3 kilohertz and 4 kilohertz. B is designed the filter, is a bandpass filter according to these parameters. Then here, N is a noise. X is a noise, which is a narrowband noise. We have this filter out this noise, but this noise has a amplitude is larger than the previous one, N. It's 2 here compared with 0.25. Then y is this x plus n going through this bandpass filter. Yx is signal x go through this bandpass filter, but it's already through the bandpass filter, so it doesn't do too much. Yn is my noise. The noise is crossing the entire bandwidth. It's a white noise. Then pass through the bandpass filter B, so we have Yn here. Then we plot this out. Plot of, let's see, so figure 1. Figure 1 is my noise n. So that across the lower picture showing the spectrum, that across the entire frequency span. Figure 2 is the signal x. Because signal x is filtered by this bandpass filter, so we do have it's a random noise, and with this passband between 0.3 and 0.4. Figure 3 is x plus n. Because n is a smaller noise, x is a bandpass noise, so we still see this effect between 0.3 and 0.4. I have this strong noise component here. Then figure 4 here is the filtered signal at the receiver side. Now because the y is filtered noise of n, and then we will see out of band component is relatively small. We only see something that's strong from 0.3 to 0.4. And then the last picture here, figure 5, is that we're comparing with the magnitude of a spectrum of signal plus noise. Those are the noise not of this signal. It's out of band noise. And the signal x is, when we generate, we are using the random generator, but it has a higher amplitude, so we assume those are the signals. So we can calculate the signal to noise ratio. The bottom picture is going through the filter, therefore the out of band noise has been attenuated. If we calculate the signal to noise ratio again, this out of band noise will be very small. So we increase the SNR. Lastly, let's look at the filter. In MATLAB, we have the function called filter. Filter B, A, and X, where B and A are vectors. They are the vectors of parameters. X is my input signal, and then I have the output is Y. Output is Y. That goes back to our general expression of a channel effect. So Yn equal to Hn convolved with Xn. So indeed, I have a convolution of my input signal sequence, and this H is the impulse response of the system, is the impulse response representing the channel. Yn is the received signal. In general, we know this channel effect or this convolution can be write out as a difference equation. So filtering, we have I from 1 to n, ai yn minus I, plus sum of I from 0 to m bi's x n minus I. So this comes from the SP. We have a signal into the channel Hn, then outputs a signal of Yn. So we can use this difference equation to represent that. And the A's and the B's, those are the coefficients of my filter or of this system, Hn. And there is a correspondence between Hn and A's, B's. In this case, now all these coefficient A's, we group them into a vector. So it's a vector of A0, A1, A2, all the way to An, where n is the order of the system, order of the channel. And then we group all these B's, B0, B1, all the way to Bm as another vector. It's column vector, transpose, column vector. And you put it here, this is A, and this is B. By default, A0 is 1. A0 is a coefficient here, so A0 is 1. In the example that we just had, we have this A is a vector of 1. So you see a B, comma 1 of X filter. That's in our previous example. This is because I don't have this term. I don't have this feedback term. Everything is coming from the input. It's a feed forward. Feed forward, then I have all these B's. They are exactly the coefficient of my FIR filter Hn. And all these B's represent the weight on each delay unit. On each delay unit that's due to the multipath. So we have here, look at this channel, it becomes a channel, it's a delayed version, X all the way to Yn. So we have a delayed one, adding here, and weighted by B1 here. And I have another delayed one. Let's just draw 2 of those. And adding here with weight of B2. So this point is Xn minus 1. So that is the delay. I have the tau exactly equal to 1 single period, T sub s. And then I have that. Now this is the delay with Xn minus 2. So I have a tau 2, the delay exactly equal to twice the same single period. And that's the second path that incoming. Adding together, I got my output signal or the received signal. So this is a filter. The MATLAB equation is if you have all these A's and B's. In this case, I only have B's. And then I can calculate the received signal of Yn. Last word on that. You can see in this case, there are some problems doing that because I only taking care of the delay. Tau is exactly the integer number of T sub s. Right? This is integer number k. In this k equal to 1, k equal to 2. What about some other delays? Well, in this case, when you receive it, because you sample exactly at the symbol period, you neglect whatever's in between 2 symbols. But in reality, maybe you need to do oversampling. So you can capture all these delayed version of delayed in a denser time period, denser than T sub s. So in this case, I assume the first path coming in, let's say x0, is here, and then the second path coming in with a delay x0, it's a delayed version x0 with a weight of b1. And then exactly delayed this tau equal to single period Ts. Then we adding together, so it gives me, adding everything together give me y, so like that. And then I have another delayed copy coming in, that's still x0 with a delay of 2 Ts. And then we weighted by b2. Then adding all these together give me the effect of whatever I have received. But as I said, in reality, we don't have that, right? You may be just in the fractional position. You have a delayed version coming here. You can do many things, either oversampling or simply because you don't sample at those rate, something in between, even though you got a delayed things coming in, you're not going to receive that. Okay, so there are many interesting things that we can work on when we add at the receiver side. But in general, a filter in this form with a convolution is how we represent the channel effect. And then indeed, we need to use a filtering or convolution or filtering to figure out the received signal.